Together, we'll study different types of hypothesis tests and discuss how you can benefit from them in your improvement projects. Also, in this module, I'll demonstrate some examples using Minitab. However, it is not mandatory that you replicate them by yourself. I'll let you know when the software may be needed. It is up to you to whether use it or not. The fact is that we don't have a specific course about Minitab at Pluralsight, and the source material for the present course is limited when it comes to it, so it is really up to you. I already said this in our first module, but it doesn't hurt to repeat. I adjusted our course, so if you choose not to use the software, this decision won't diminish your chances of approval in the Green Belt certification exam. Back to this module's content and what is in for you by taking it. Hypothesis tests are statistical tools used to draw conclusions based on data. With a basic understanding of the process and process performance, as well as real-time data or as close to real-time data as possible, Lean Six Sigma teams can draw statistical conclusions that are extremely accurate if they ensure that the measurement systems are good, have the right sample size, and know how to set up the right type of hypothesis test. In this module, we'll talk about different types of hypothesis tests, how to set them up, and how to read the results. We'll cover how to choose the right sample size for various data types and hypothesis tests. You can also run some tests in Excel using the analysis toolpack you previously downloaded. But what exactly is the content we're going to explore together? Let me break it down for you. We'll start by studying basic hypothesis tests, also null, alternative, and right hypothesis tests. I'll teach you more about hypothesis tests for discrete data, proportion tests. I'll also demonstrate a one-sample t-test example and the chi-square test, but that's not all. We're also going to cover two sample tests, the Mann-Whitney test, considerations regarding how to run hypothesis tests, and at last, we'll discuss how hypothesis tests can be applied into the DMake methodology. Now, if you want to know more about each of the hypothesis tests I listed in this video, just keep watching our course. And talking about this course, remember, it is 100% based in the Lean Six Sigma Green Belt Certification Training Manual, which content was used with permission from the Council for Six Sigma Certification. You can download the training manual for free at sixsigmacouncil.org. This is an audio and visual representation of the official Green Belt publication produced based on Pluralsight instructional design guidelines and templates. In this video, we're going to talk about the basics of hypothesis testing. Hypothesis tests cover three broad categories: testing whether the data you have fits a data model. In our previous course, we conducted a hypothesis test to determine whether data fit in the normal curve, and we used the chi-squared goodness of fit test, but ultimately it was just a hypothesis test. But there are more categories. You can also compare a statistic to a hypothesis about the data or population, and answering the question whether something changed within the data, often after a team has modified an input or other part of the process. In the case of most Lean Six Sigma projects, the team probably wants to find out whether the process or outcome is improved or not. While the type of hypothesis test you use depends on the answers you are seeking and the type of data you have, all of the tests follow essentially the same guidelines. You begin with a statistic or criteria that you will usually compute from your sample data. You create a null hypothesis and an alternate hypothesis in keeping with the type of test you are dealing with. And remember, when we ran in our previous course the chi-squared goodness of fit test, the null hypothesis was that the data was normal. The alternate hypothesis was that the data was not normal. The statistic or criteria is compared against a reference criteria or distribution. And how the calculated statistics compares to the reference criteria determines whether you accept the null hypothesis or reject the null hypothesis in favor of the alternative hypothesis. Hypothesis tests are a large part of inferential statistics, where we draw conclusions about the overall process or population by analyzing the sample data and measurements. When stating hypothesis, we are not making statements about the sample, we are making statements about the population or entire process. For example, a hypothesis could be, the population mean is 5. We don't need to make a hypothesis about the sample mean, we can calculate the sample mean. In this video, we're going to study null, alternative, and right hypothesis tests. The alternative hypothesis is abbreviated as HA and is usually a statement that is likely to be true if the null hypothesis is not true. The alternative hypothesis in our previous examples in previous courses was there is a statistical difference between the distribution of our data and the distribution of data on the normal curve. In short, if we reject the null hypothesis, we accept the alternative hypothesis, in this case, that our data is not normal. The alternative hypothesis is typically written as not equals, a greater than, or a less than statement. The mean of this new process is greater than the mean of the old process. The distribution of the data is not equal to the normal curve. How you write the alternative hypothesis depends on the question you are asking and the type of hypothesis test you are running. Typically, the null hypothesis is an equal statement of some type. The mean of the new process is equal to the mean of the old or even the new process. The distribution of the data is equal to the normal curve. Anytime you draw inferences about a population from sample data, there is at least some likelihood of error. With hypothesis testing, errors come in two types. Type 1 error. The null hypothesis is rejected when it's actually true. It is also called the producer risk, and the probability of the risk is measured by alpha, where alpha is a probability between 0 and 1. Type 2 error. The null hypothesis is accepted when it is actually false. It is also called the consumer risk, and the probability of the risk is measured by beta, where beta is a probability between 0 and 1. To describe the risk and set up our hypothesis test for what we deem to be an acceptable risk, a confidence level must be picked. The most common confidence level uses 95%, where alpha equals 0.05. Typically, the confidence level is set with type 1 error in mind, so you use alpha for the confidence level. The value of beta then contributes to the sample size requirements and the power. Sample size will be covered in the next videos. To determine which hypothesis test to run, you must know which type of data you have, continuous, variable, or discrete, and even attribute. The number of levels of interest for the input in question, if it's 1, 2, or even more. The distribution of the data, if it's normal or non-normal. And what you are testing, means, medians, variance, count, or proportions. The hypothesis tests we're going to cover in this module deal with 1 or 2 levels of interest. In the following videos, we'll introduce various types of hypothesis tests. Then, we'll walk through running some of these tests. In this video, we're going to study hypothesis tests for discrete data. The hypothesis test is set up as null alternative stands for p-sample equals p-target, while the alternative hypothesis is p-sample, which is different from the target. Note that in the setup I just presented, the alternative hypothesis is set in a default to non-equal or not equal. If you are using Minitab, it allows you to adjust the alternative hypothesis to a greater than or less than scenario if desired. Let's take a look at an example together. A school administrator believes that the students in a certain classroom are being affected by some environmental issue with that room. The administrator wants to see if the students in that room perform statistically lower on tests than the students throughout the school. She has already noted that different classes in that room are taught by other teachers who also teach in the other rooms, which means she ruled out a teacher influence. The administrator gathers data. The rate of failure for classes taught in any other classroom is 20%. Out of 142 students who have a class in the classroom in question, 38 are failing that particular class. The hypothesis test will be reading out with both a real-world statement and a statistical statement for both a null and alternative hypothesis. Null hypothesis would be there is no difference in the failure rate between the classes taught in that specific classroom and those taught elsewhere. And here is how we can represent it mathematically. The alternative hypothesis is that the rate of failure is greater for those classes taught in the specific classroom, and you can represent the hypothesis test as I am presenting it on your screen. In this video, we're going to study proportion tests. Proportion tests are used when there is only one factor for x. They're also used when there are two levels of interest for x, the input being x. Typically, there are two sets of data regarding the input and you are comparing those two sets of data. Proportion tests are also used when comparing proportions, percentage, rates, for example, between samples or between samples and a target. If you want to try, you can use Minitab because proportion tests are available on it. Let's think about a hypothesis test that is set up as I am presenting on your screen. And this is something we have seen before. Note that in the setup I am presenting, the alternative hypothesis is set in a default to not equal. Minitab allows you to adjust the alternative hypothesis to a greater than or less than scenario if desired, as I previously also explained to you. Reconsider the example I offered you about the school administrator in the classroom in our previous video. Perhaps the school administrator determines that students in that classroom do, in fact, perform statistically differently from students in other classrooms. The administrator makes a decision to move the students in that classroom to another classroom. She then gathers data about test performance in the new classroom. Now, the administrator has two sets of test performance data for the same students. The only variable that has changed is the classroom location. She wants to know, is there a difference between performance in the old room versus the new room? The null hypothesis states that there is no difference in the failure rate between the old room and the new room. Here is how we can demonstrate that. And the alternative hypothesis states that the rate of failure is less in the new classroom. Once more, this is how you can demonstrate the alternative hypothesis. In this video, we're going to study one-sample t-test. Let's get to know the one-sample t-test, or also known as the paired t-test. It is used when comparing means, and it's also typically used when dealing with smaller samples or when standard deviation is known. One-sample t-test compares the mean of a sample to a target mean. When dealing with larger samples or when standard deviation is not known, use the one-sample z-test. Paired t-test compares the mean of a sample against the mean of another sample for the same factor of x. Usually, the first sample is the baseline and the second sample is taken after a change is made. The test is run to see if the change made a difference. One-sample t-test is available in Minitab. It requires the standard deviation, mean, and sample size, as well as the target, or hypothesized mean, for calculations to really happen. Paired t-test is available in Minitab and Excel's Analysis Toolpack. The hypothesis test can be set up as the following. Note that in this setup, the alternative hypothesis is set in a default to not equal. As previously mentioned, Minitab allows you to adjust the alternative hypothesis to a greater than or less than scenario if desired. Let's study with an example. An agriculture company growing corn produced an average of 168 bushels of corn per acre each year for 5 years. The company made a change to its seeding process in an attempt to increase the yield of its fields. The harvest following the seed change resulted in an average of 175 bushels of corn per acre each year. Now let me ask you something. Did the seeding change result in a statistically different outcome in yield per acre? The null hypothesis is that there is no difference between the outcome after the seeding change and the outcome before it. At last, the alternative hypothesis states that the seeding change resulted in an increase in the average amount yielded per field. And here it is. In this video, we're going to study the chi-square test. It is often used when comparing standard deviation or variance. It compares the standard deviation or variance between two samples of the same x factor. Usually one sample is taken after a change to the process has been made, or compares the standard deviation or variance to a target or hypothesized statistic. This is a test that is available in Minitab and requires sample data in two columns or summary data to include sample size with either sample standard deviation or sample variance and hypothesized standard deviation or variance. You can see the hypothesis test set up in your screen. Note that in the above setup, the alternative hypothesis is set in a default to not equal. Let's work an example. A manufacturing plant makes the wheels that are put on dolly charts. The plant provides 3 sizes of wheels to a partner plant, which makes the dolly itself and uses wheels to complete the process. The partner plant makes a complaint. The smallest wheels coming from the factory have enough variation in size to cause stability problems with the final product, resulting in defective dollies or wasted wheel parts. The wheel-making plant launches a Lean Six Sigma improvement project to reduce the variation of the size in the smallest wheels. The team measures for a baseline and finds that the standard deviation in the size of the wheels is 0.0409. The team makes changes to the process and measures again to compare the new standard deviation to the old. The new hypothesis is that there is no difference between the standard deviation. The changes did nothing to statistically reduce the variation in the process. And here we can see the standard deviation once more. The alternative hypothesis states that the improvements reduce the standard deviation in the process. And here we have it. In this video, we're going to study the two-sample t-test. The two-sample t-test is used when comparing means. It compares the means between two samples of different X factors. This test is available in Minitab and Excel and requires sample data in two columns or summary data to include sample size, sample mean, and standard deviation for both samples. It also requires you to know whether equal variances between the two samples are assumed or not. The two-sample t-test might seem like the one-sample t-test because in the one-sample t-test, we discussed how you might compare a sample from before a change to a sample from after a change. However, the two-sample t-test is slightly different because you are comparing two samples from different populations. For example, you might compare the mean body temperature for children who didn't receive the influenza vaccine to mean body temperature for children who did receive the vaccine. This is different than comparing mean body temperature for the same group of children from last year when they didn't receive the vaccine to this year when they did receive the vaccine. The first example would use the two-sample t-test. The second example, year over year, would use the one-sample t-test. And here we have the hypothesis test already set up. Two attorneys practicing the same law firm are turning in very different amounts of billable hours, even though the partners know that the two lawyers have similar caseloads. One partner hypothesized that attorney's A legal staff is taking too long to handle some tasks, because the firm bills at a certain time for administrative-style tasks regardless of how long these tasks take. If legal staff is taking too long for such tasks, they are spending time on work that can't be billed for. To test the theory, data is gathered about the time legal staff spends on tasks. Specifically, a team looks at time spent on 3 tasks for which the legal staff is allowed to bill 15 minutes each. Certain types of simple administrative phone, copying, or filling tasks. So the null hypothesis is that there's no difference between the average time attorney A staff takes and the average time attorney B staff takes for such tasks. And here we have the null hypothesis set up. The alternative hypothesis is that attorneys B staff takes on average less time for these tasks. And here you have the representation of the alternative hypothesis. In this video, we're going to study the Mann-Whitney test. This test is used when comparing medians. It compares the medians between samples of two factors of X. It is available in Minitab and requires sample data in columns. And the hypothesis test is set up as you can see on your screen. It's not really hard to read now that you understand more about hypothesis tests, isn't it? Here we have a null hypothesis and an alternative hypothesis. Let's consider another example. Imagine a real estate company that has limited resources. They can only launch a campaign for one neighborhood at a time. So to maximize potential results of their first campaign, the company wants to choose the neighborhood with the highest number of bedrooms and the highest number of homes. The company gathers information about homes in two neighborhoods. They then compare the samples to determine whether one sample has a statistically higher median number of bedrooms. The null hypothesis is that the median number of bedrooms in neighborhood A is equal to the median number of bedrooms in neighborhood B. That's how we can represent the Mann-Whitney test. The alternative hypothesis states that the median number of bedrooms in neighborhood A is higher than in the neighborhood B. So here we have it. In this video, we're going to consider the reasons why running hypothesis tests is important. At this point, a common question about hypothesis tests comes up. Why go through the trouble to run a statistical test to determine if things are different? Consider this example based on the one-sample t-test. An agriculture company growing corn produced an average of 168 bushels of corn per acre each year for 5 years. We've seen this before. The company made a change to its seeding process in an attempt to increase the yield of its fields. The harvest following the seed change resulted in an average of 175 bushels of corn per acre each year. Did the seeding change result in a statistically different outcome in yield per acre? The question is the mean corn yield per acre statistically higher following the seed change? Just looking at the numbers presented in this problem, we can see that the mean following the seed change is 175. When you compare that to 168, it is obviously higher. Why will we go through the trouble of setting up and running a hypothesis test? We noted that it's not always enough to see that a histogram appears to be symmetric and following the normal curve. Raw data can be deceptive, which is why we run the chi-squared goodness of fit test in Excel to ensure the data was normal. The same principle is true when comparing statistics from samples. Yes, 175 is higher than 168, but in the case of the corn yield, is it statistically different? Lean Six Sigma teams can't just answer the question, is this number different? They must answer the question, is this number so statistically different that we can't take action on this information? Statistically different doesn't have to do with scale. In one process, the difference between 10 and 23 might not be statistically different. In another, the difference between 10 and 10.5 might be statistically different. To run a hypothesis test, you typically follow the same series of steps. First, you state the null alternative hypothesis. The null hypothesis is always written from the perspective that no change or difference occurs or is present. The alternative hypothesis is always written from the perspective that a change or difference is present, either not equal, greater than, or less than. The next step in most hypothesis tests will be to set a confidence level for alpha. Usually the confidence level is set at 95% for alpha, but other common settings are 99 and 99.9%. A confidence level of 95% means an alpha value of 0.05. A confidence interval level of 99% means an alpha value of 0.01. And a confidence interval of 99.9% means an alpha value of 0.001. Next, practitioners usually decide which hypothesis tests they are going to use. And to make such decision, professionals will analyze the type of data they have, the statistic they are dealing with, and how many sets of data they have. Next, if you are running a hypothesis test, you probably will decide whether your sample size is fixed or whether you can select a sample size based on your beta setting. Then, you'll most likely use a software like Minitab to run the test. Next, you'll interpret the p-value against your alpha setting, which tells you whether or not to reject the null hypothesis. Finally, you'll translate the statistical analysis into real-world, business-relevant language. For each statistical test, the calculations handled automatically in Minitab or other softwares return several values. Some calculations, such as the chi-squared test, return specific statistics. In the case of the chi-squared test, that statistic is the chi-squared value. These statistics can be valuable in applications and analysis, but for the purpose of hypothesis testing, we are primarily concerned with the p-value. The p-value is returned for each test, and we compare the p-value to the alpha value we set before we ran the test. If the p-value returned for a test is less than the alpha value you set, then you reject the null hypothesis and accept the alternative hypothesis. If the p-value returned is more than the alpha value you set, then you fail to reject the null hypothesis and you do reject the alternative hypothesis. We talked about setting a confidence interval for alpha. If the confidence interval is 95%, then the alpha value is 0.05. Given a p-value of 0.02, we would reject the null hypothesis and accept the alternative. And given a p-value of 0.13, we would fail to reject the null hypothesis and would reject the alternative. In this video, we're going to consider how hypothesis testing can and should be used alongside the DMAIC methodology. For Lean Six Sigma teams, hypothesis testing is an activity typically found in the later three phases of a DMAIC project, and most specifically in Analyze or Improve. During Analyze, teams might use hypothesis testing to help determine if certain inputs or factors could be a root cause. Given historical data, teams who can separate factors within a process can use that data to run a hypothesis test. For example, a team might believe that one employee is responsible for defects in a process. By comparing defects rates when that employee is on shift to defect rates when the employee is not working, teams can draw conclusions from data. During Improve, hypothesis tests are often used to validate solutions that are being tested in beta environments or in small batches. The team compares the results of that solution with previous data about the process to determine whether the solution has created a statistically different result and whether that result is what the team wanted. A hypothesis test can begin to sound very mathematical. It's important to start with a business-friendly statement and then with a business-relevant statement regarding the conclusions. In the next module, I'll share with you tips for converting various Six Sigma and statistical conclusions to business-friendly presentations and knowledge, which is especially helpful when a Lean Six Sigma team is proposing changes based on statistical analysis. The ability to convert that analysis into business-friendly language helps teams explain to decision makers why a change is likely to help. This module introduced a lot of new statistical terms, many of which will come up again in future videos. Before moving to the next videos, take a few minutes to review the terms that came up in this module. Starting by the null hypothesis, which is the assumed hypothesis, the statement that nothing has changed, or no statistical difference exists. This is like the innocent verdict in a criminal court. It is assumed unless evidence tells us otherwise. The alternative hypothesis is the statement that something has changed or is statistically different. It can be framed as not equal, greater than, or less than. If evidence means rejecting the null hypothesis, then the alternative hypothesis is assumed to be true. I also introduced you to the concept of alpha, which is the measurement of the risk of a type 1 error, the error that occurs if the null hypothesis is rejected when it was actually true. We also studied beta, which is the measurement of the risk of a type 2 error, the error that occurs if the null hypothesis is not rejected when it was actually false. We covered test statistic, a standard value that is used to calculate the p-value to determine whether to reject the null hypothesis. For example, in the t-test, the value is t. We didn't calculate or discuss these values in details, but they are shown in Minitab's output screen and can be valuable for more advanced statistical calculations. When using Minitab for hypothesis testing, the p-value is automatically generated. We also spoke about the p-value, and the p-value is the number typically used to compare to the alpha value to determine whether or not to reject the null hypothesis. The null hypothesis is rejected if the p-value is less than the alpha value. That's it for now. I'll see you in our next module.